All right, I'm going to go ahead and get us started. Hello, everyone, and welcome to the UFS webinar. This webinar is hosted by the National Weather Service, Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS, both research and operational settings. My name is Alex Alder, and I'm here to help coordinate and deliver the webinar. Please feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, you can email your recommendations to us at ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you'll be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that will be provided in the chat box shortly. Presentations last about 45 minutes, followed by Q&A for about 15 minutes. And again, there will be a Google document sent out that you can type your chat questions into, and we will go over them after the webinar. For today's webinar, we are learning about the novel grid capabilities in GFDL's Dynamical Core FV3 by Dr. Joseph Muallim with Princeton University and GFDL NOAA. Joseph is a computational scientist, research engineer currently working at the Weather and Climate Division of GFDL and NOAA and the Cooperative Institute of Modeling the Earth System at Princeton University. In 2014, as part of a dual degree program, he earned his BSc in Mechanical Engineering from the Lebanese University in 2014 and an MSc in Fluid Mechanics from the National Institute of Applied Science in Lyon, France. In 2018, he completed his PhD in Mechanical Engineering, specializing in thermal and fluid scientists from the University of Sao Paulo, Brazil, supported by a National Scholarship Award. He then joined the Department of Mechanical and Mechatronics Engineering at the University of Waterloo, Canada, as a postdoctoral fellow and session lecturer, focusing on fluid mechanics until early 2020 when he joined GFDL. At Princeton and GFDL, he is currently developing new numerical technologies and algorithms in GFDL's Dynamical Core FV3. And I'm going to turn it over to Joseph.
Alex. Hello, can you hear me well?
Yep, we can hear you. And
okay, 1 second. Can you see my screen?
Yes, we can see your screen. Perfect.
Okay, great. So hello, everyone. Thanks, Alex, for the invite and introduction. It is my pleasure today to talk about new grid technologies that you have been working on in FV3 here at GFDL. So first, I would like to acknowledge many people who directly contributed and indirectly as well to this project, namely Lucas Harris, Rusty Benson, and many people in the FV3 and the MST teams. So in today's talk, I will basically present two topics, grid nesting and the GeoGrid. So basically, many of you are already familiar with FV3, so I will jump right away and talk about grid nesting. So it is still impractical to operationally run ultra-high resolution models at scales needed to resolve small-scale flow features to accurately predict special weather events such as severe storms and hurricanes. Even if we do that, there is an issue with data. So we can generate a lot of data, and it's not too easy to manage, store, transfer, and share the data. So in FV3, we have different variable resolution techniques already implemented in the code. We have grid nesting on the left and grid stretching on the right. So grid nesting is basically where we add an additional grid over an area of interest, starting from a cubed sphere grid. Then we can add here this red rectangle, which is an additional tile or grid, we call it, over, for instance, here CONUS to simulate severe weather predictions. So here, this is a snapshot of our sea shield configuration, basically a 13-kilometer global domain with a nest of around 2.5 kilometers for severe weather prediction. We have another configuration here called T-shield, where we have this very large nest over the Atlantic for tropical cyclones. For the grid stretching technology, basically, we take the cubed sphere and we can stretch one grid to get very high resolutions. It depends on the stretch ratio and what the user is interested in. So my colleague Kai has been working on this project, and he was able to basically run idealized test cases of a supercell thunderstorm and simulate some kind like tornadoes at 1 kilometer and 500 meters. Also, there's this new model that's being developed, which is a version of AM4 using this stretched grid with a highly stretched grid over the US with an effective resolution of 13 kilometers that is described in this very recent paper here. So basically, nesting started in FE3 with Harris and Lin in 2013, where one tile was implemented in the code. So you can see here, these squares represent the different faces of the cubed sphere, the 6 faces, and here we can add one additional tile, as you can see in this picture. So we have upgraded this technology to basically accommodate different or multiple same level and telescopic nests. So everything that I'm about to show today is basically documented in this paper. And what you see here is a configuration where we have 5 additional nests. We have 3 same level nests, as you can see here, one on the East Coast, one on the West Coast, and one on the Pacific. And we can also add a nest within a nest. We call that telescopic nesting. And here we have one telescopic nesting here, the red one, and another telescopic nest focusing here on this region to simulate landfall of hurricanes. So basically the framework is very flexible and the user can add as many nests as they desire. So here I will have a quick or brief overview of how nesting works in FE3. So on the top right, we have a parent grid, and on the bottom right, we have a nested grid. And here on the left, we have the different level of time stepping in FE3. Basically, we have 3 level of time stepping: the long time step, a remapping time step, and the fastest time step, which is the acoustic time step. So what we do here is basically initially when we start with the nesting algorithm, at the end of the long time step, before starting the remapping time step, we fill the data here in region 4 from the compute domain of the top parent grid, which is 1. We do that by simply applying a linear interpolation in space to all the variables here from 1 to 4. Then each grid will run on a different set of processors. I'll talk about that later. And at this time, for instance, at the acoustic or shortest time step, the region for the data in region 4 is basically extrapolated in time. So it's not fixed. So we update the data here, which is in region 4, every long time step. But then for the acoustic time step, the shortest time step, we do extrapolation in time just to minimize the MPI communication between the processors. So in theory, an extrapolation is not the best, but in practice, it doesn't really degrade the solution or introduce a lot of meaningful errors. And at the end of the nesting algorithm, we have an option if the user desire where called a two-way updating, where basically the data here averaged on of region 3 and replaces the data of region 1 here, where the nest is actually located. So this framework is also flexible. The user can choose the variables that they are interested in, and they can do this two-way update. In our case, by default, we update the temperature and the 3 winds. In this way, basically, we conserve mass on the parent grid, so there's no violation of mass conservation on the top parent grid if we don't update mass. It's worth noting that on the nets we don't have this conservation because of all the interpolation and extrapolation that we are performing. So for the two-way updates for cell mean scalars, for instance, if we consider the temperature or pressure in these small squares, we do an area-weighted average for the variables here inside the small square to get their average for the big square here. And for the winds, for instance, the degrid winds that you see here, basically they are tangent to the grid edge. And what we do here is we do a length-weighted average of here, for instance, the small yellow arrows will give us this big arrow for the coarse grid result. So it's worth noting here that for a cubed sphere, the grid cells are not squares. This is a simple schematic, and the algorithm basically can be applied to any non-orthogonal quadrilateral grid. Some features of nesting that we have already in the public release in FE3. Basically, we have vertical nesting is implemented and allowed. So that means that the nests can have a lower model top, a different model top. For instance, in our T-shield configuration, the shield configuration where we simulate tropical cyclones, we have more horizontal layers. We have 75 layers, and then the model top is at 200 Pascal, where the top band grid has 63 layers with a model top at 64 Pascal. At the moment, the nests cannot cross a cube sphere edge or corner, although the FMS libraries that are developed by the modeling system division at GFTL support an edge crossing. But we haven't implemented that in FE3 yet, so the nest has to be confined within one of the cubed sphere faces. Each nested grid can run on a specific list of processors. So basically, at the beginning of a simulation, we distribute the processors over the different grids, so the user can specify how many processors he will need on each grid. And that will make the algorithm very computationally efficient and allow for load balancing on each grid. Otherwise, things like telescopic nesting, if you do a serial computation, will not be very efficient. We can configure each nest differently with its own. It will have their own input name list. You can run different time steps, different parameterization on each nest. The two-way updates can be turned on and off on each grid. We don't apply extra relaxation at the nest boundary conditions. And the nest can be also implemented in a stretched parent grid. And for the last point here is the algorithm. We try to make it bit for bit reproducible. At the moment, it is that way. So spend a lot of time to make sure that reproducibility is conserved, especially when basically when you change the processor layouts on the parent and nested grid and using very irregular domains. We try to we worked very hard to make this algorithm reproducible, and it wasn't very straightforward to do that. So I will show you some results for simulation for the landfall of Hurricane Laura of 2020. So basically here, this is a schematic, just a demo to show you how nesting can work and how you could basically use it for instance, for the hurricane landfalls. So we start here from a 13-kilometer global domain, and we add a triple nest telescopic configuration. Basically, we will have a first grid with a refinement ratio of 3, so we will have an effective resolution of 4 kilometers. A first telescoping nest with a 1.4 kilometer grid, and then a third telescoping nest at 500 meters. So you can do something like this. You can go even higher from a perspective of the computational framework. You can use as many nests as you want. So here I will show you the results on the 13-kilometer grid. So what you see here is the integrated column water vapor. So this is basically the resolution similar to SHIELD and GFS. Here we are looking at the simulation results at 4 kilometers. We are basically looking at the first nest in this configuration. And you can already see that I'm hoping you are able to see this simulation as smoothly as possible. You can already see some fine structure and more details in this snapshot here at 4 kilometers compared to the 13 kilometer. And then here also, this is the 1.4 kilometer result on the telescopic nest. And the 500 nest simulation wasn't very stable at the moment, and we are working in progress to basically try to tune the model and make it work to get accurate simulation and meaningful results. So this is here just to show you how the framework can work and what kind of configuration you can use when nesting. And I will leave it to my colleague to really use the right schemes and right equation to get the correct behavior of the hurricane. So let's step back and look at a 200 kilometer simulation. Here, there's the field that you are looking at is the vorticity at 850 MB, and you can clearly see that the hurricane here starts here and then spake very quickly even before reaching land. And then we will have this configuration where we add 4 different nests, 3 same level nests, one over the east coast, on the west coast, and one in the Pacific, and 1 telescopic nest here, the big red one over the east coast, as you can see here, the grid layout. And what you see here is we are still at the top parent grid at the 200 kilometer resolution, and you can see the effect of the two-way update. We are still able to get the landfall of the hurricane, and you can see it how it jumps between the grid cells, which are very, very coarse. And you can see where the nest resides. We can capture different weather events at the same time. So basically, we have the hurricane Laura. We have some intense activity here at the west coast of Mexico. We have the initial phases of Typhoon Maisa, and we are able to accurately or to capture these events with a very simple configuration starting from a 200 kilometer global resolution. So if we take a look here at the computational expenses, and there are more of this in the paper, basically for a 200 kilometer resolution, you can basically run it for 3 days, 200 cores, 80 seconds. It's very fast simulation. When you go to 13 kilometer, you will need a 13 kilometer global simulation. You will need more processors. The files will become larger naturally, and the simulation will take more time. And if you take a look here at this configuration with the number of points and the number of processors on each grid, so you can notice that the red nest here basically is at 12 kilometer, which is similar to the 13 global resolution, and we are able to simulate basically the same event with less processors, less data, and basically less resources. So this project was initially funded by the Hurricane Supplemental Project, and we have transferred this technology to HAFS, which became operational in June 28 of last year. Some other fields that one can look at, for instance, precipitation, the winds at 1 kilometer that you see here. And we have also this capability working in a regional domain. So in the paper, we show also an atmospheric river that hit California in 2021 in a regional configuration, starting by a top parent grid of 50 kilometer, a first nest at 17 kilometer, and a telescopic nest here at 6 kilometer. And basically going down in resolution, we can capture finer detail, and we are able to see here basically that the edges of the nest don't really interfere or disturb the structure that are present in the simulation. So some ongoing work that we have been doing over the last year, we have developed this framework where we're trying to simulate idealized hurricane in doubly periodic domains. Basically here we have a domain, a 16 by 16 degrees with an effective resolution of 2 kilometer, with the first nest here at 500 meters covering the entire region of the hurricane, the inner core and the eye. and then another nest down to 100 meter, also here covering the eye. And this work was basically focusing on, we are trying to go as high as possible in resolution to see what we can capture. And my colleague Poon has been able to capture, we call them finger-like clouds in the inner core region of the hurricane. So to our knowledge, this is the first time that we are able to simulate the entire intensification period of a hurricane over the whole hurricane. And we are discussing in this paper these features. So this paper is accepted and it will be available soon on GRL. And on the right, a nice animation at 500 meter by my colleague Poon to show what kind of results we expect from this configuration. So more ongoing nesting projects. We are working on a version of Shield called Teleshield, where we employ a telescoping nest to focus on different areas of interest. For instance, my colleague Janui is using this telescopic nest to study precipitation, heavy precipitation over Taiwan. We are also looking on having a nest here over the northeast corridor at 1.4 kilometer. We are also still working on this double periodic tropical cyclone setup. We are aiming for even higher resolution. We are trying to implement some subgrid turbulence scheme and LES to get more meaningful results at higher resolutions. We are working with our partners at AOML to implement moving nest capability for the multiple nests. So here in this animation, you see two nests that track a storm and move with it. And we are also working to have the telescoping nesting also move following the storm. And here in the bottom right, this is a schematic from our colleagues at the Mars Climate Modeling Center at NASA, where in their climate model, they use FE3 as their dynamical core, and we're using nesting to study potential areas of interest on Mars, basically potential landing sites for future human exploration trips. So this was a quick overview for nesting. So I will talk about, so all the nesting code is available online and can be used, basically can be downloaded directly from GitHub. For the GeoGrid, this is still a work in progress. So I will start by showing this slide or these images taken from this really nice paper by Williamson from 2007, where basically different grids are discussed. And the idea here is basically no grid is perfect. And to solve the equation of motions on a sphere, we have to discretize this equation using some grid geometry. And different people have been trying different grids for a long time. And there is no clear winner. For instance, the Canadian operational model is using the yin-yang grid. The German ICON model is using the icosahedral grid. The European model is using the octahedral grid. For us, we are using the cubed sphere grid, which we transitioned from a previous Latron grid, which the Met Office is also doing now at the moment. So FE3 was called FV before switching to the cubed sphere. So it was employing a latitude-longitude grid. And when it switched to a cubed sphere, it became FE3. 3 is for the cube. So there was many reasons for this switch. So basically, the latitude-longitude grid is a very nice grid for our problem, but it's not very efficient numerically and computationally. So basically, because of the convergence of meridional lines here, you can see that the area becomes very small, and that will have a restriction on the time step to accommodate or to not violate the CFL condition. And basically, for higher resolution, we have smaller and smaller areas here, and we can't really have a long time step to really run the model efficiently. And it's not very straightforward to decompose this model on HPC systems. On the other hand, the cubed sphere grid doesn't have these issues. Basically, we have a quasi-uniform resolution, a a good aspect ratio over the whole globe. It's very scalable friendly. So if you take a look here at one of the faces, you can easily decompose it, and basically each processor will take care of different points here. Like very easy to scale it on HPC systems as well, which is much better in terms of if you are interested in efficient ultra-high resolution modeling compared to a latitude longitude grid. However, one disadvantage is instead of 2 major singularities at the pole, we have now 8 minor singularities at the cube corners, and also singularities at the edges of the cube face, the lines between the corners. So let me skip this and then go here and show you how we place the variable. And you will see in a moment why I am presenting this. So how the variables are actually placed on the grid. So for different numerical reasons, over the years in FE3, we basically use different variables at different locations. For instance, if we have a scalar variable like the pressure, temperature, or vorticity, it's a cell-centered variable on the A grid. We also have the winds at UA and VA at the center for the physics schemes. For numerical reasons, we have the kinetic energy and divergence at the corner. And we also have the C grid and the D grid winds, as you can see here. So basically, the C grid winds are really nice for the finite volume discretization. So if you take a look here, it's a natural description. It's very naturally described the fluxes here. And the D grid wind are important when it comes to quantities like vorticity, because we can simply apply a green theorem here and basically integrate over a closed surface and get the exact value of the vorticity. So the SJ's philosophy was to using the CD grid together is better than a pure C and a pure D, and for the different reasons that we are presented on the slide and in his paper. So if you are interested, please check SJ's paper. So what is the GeoGrid then? So it's not the CD grid system, but I will show you why. I also talked about them later. It's a solution for grid imprinting. So if you're not familiar with grid imprinting, basically grid imprinting is when there is a discontinuity in the grid, that discontinuity in the grid will generate artifact at noise in the numerical solution. So if we are integrating over grid lines, and then one of these grid lines has a discontinuity, then that discontinuity will also manifest as, or will cause a discontinuity in the numerical solution. And then we will see the shape of the grid in the numerical field. Thus the name grid imprinting. So the goal of the GeoGrid was to basically find a solution to grid imprinting that's better than the current edge handling code that's already present in FE3. So here I'm showing you a snapshot or a plot here for the omega field, which is average over some time in one of our models. So I will give you a second to try to identify grid imprinting if you look at this figure. So basically this is taken from Spear at 25 kilometers. And if you look closely, you will see here the edges and basically here the corners and the edges in this field, which is basically not desired. And this is noise that we should basically eliminate. So this is grid imprinting. We are seeing the structure of the grid in the model. And this has been also reported in Ning Zhao's paper of 2018 in the AM3 and AM4 model, where they found some distortion in precipitation in few months. And they had to really look into this issue to really find this issue. So it's not too straightforward to find. So you have to really know what you are looking for, and you want to try to find it. So let's take a step back and look at the causes of grid imprinting and how it occurs. So basically here we are looking at one of the faces of the cube sphere, and imagine our compute domain here is the blue domain on this face, and we take neighboring data from the red region here from neighboring faces for our abstraction scheme. So imagine we are we are integrating over one of these grid lines, the yellow dashed line. So when we reach here the edge, you can see there's a kink in the grid. So if we are integrating and we get to this point, then there's this discontinuity here, and then a shift in direction to go along this line here. So that basically, that structure basically causes the issue of grid imprinting in that you have seen in the previous figure. So in FE3, if you just open any file, you will see a lot of code like this, where call this like the edge handling code, where at every edge we have some special operation to minimize this effect. So this is basically at the northern edge, this code here at the east edge. We have to also fill the corner data, which is not present, not existent in a cubed sphere structure that I will show later, and which is usually the data is copied from one of the neighboring faces. So what we did here is basically we took this cubed sphere kinked structure and we unfolded the area in the halo region in a way that if we are integrating along one of these lines, we continue the integration over the extension of these grid lines onto the neighboring face. So we call this, so this is the difference between the two. So this is the original grid, and this is where we actually integrate using the geogrid. So basically, when we get here to the edge, there is no discontinuity in the grid, and we can just continuously integrate without any interruption. On the left, we will call this the kink grid, the original grid that is used in FE3. And here on the right, this is the extended grid, which is a combination of the kink grid and the geogrid is the combination of the kink grid and the extended grid. So what we do is basically imagine we have a processor here. It will take the data from the neighboring face, which will remap it along the extended grid, and then it will give it back in the algorithm. So basically using the extended grid and the combination of both these grids, we can integrate without any interruption at the grids. We have written all these algorithms in the message passing calls, so other users and developer will not have to worry about this. And one additional advantage that we got out of this is basically to minimize the data movement on CPU, GPU hybrid systems, which will be a stepping stone for future FE3 development on GPUs. So basically, given that we are integrating now without any interruption and without any of those if statements that I showed you before, so this is basically the best way to approach the GPU problem in terms of efficiency. So for the GPU, the best scenario that we can get is basically we perform the same operation on a lot of data. So if we don't have if statements, we are basically performing the same operation over the whole data, which will give us a lot of speed ups when we switch to the GPU systems. And one thing here is this corner region that you can see that's now presented in the extended grid, and I will talk a little bit about later. So there were too many challenges to get this algorithm to work. Basically, Shichen wrote an initial version of the geogrid for self-centered variables when he was at GFTL, so he had to extend in his dynamical course. So we had to take that algorithm and extend it to support different variables location, that the one that I showed you before, the B, C, D grid locations. We had to implement a corner handling algorithm to accommodate the 2D transport scheme. We had to break down highly optimized routines such as the shallow water solver on the D grid to apply flux averaging, and I will show a slide about that later, and basically bypass all the edge handling code that present in the solver. So here I will show you, for instance, how we remap, or how, for instance, if we have a D grid wind, how we remap them using the geogrid. So if you are so this is a little bit technical. If you are a developer, you might be interested in this. Basically, if we are taking a look at the north edge region of a face here, so basically this is the north, this is the edge. This is how the D grid winds are placed in the halo region. And on a so this grid can be rotated randomly on the latitude longitude coordinate. So in FET we have local coordinates on each face of the cubed sphere. So first we have to project these components to the same location so we can build the velocity vector in one location. Then what we will do is basically we will rotate the velocity vector and to the Earth relative zonal and meridional to get the Earth relative zonal and meridional wind on the latitude longitude grid for all the faces. What we will do next, we will consider a fourth halo layer. So in FET, we currently use 3 layers because of the numerical scheme, and then for the view grid, we have to take 4 layers into account because we will need some data outside of this outside of the third layer to basically get a correct value of the arrow here that's represented at the extreme edge. So now we consider an extra halo layer. We do the remapping. So we compute the data where it's supposed to be on the extension of the great circle lines. Then we will rotate the data back to the local coordinates, and then we will compute the resulting field to get the final remapped d-wind field. So this is not straightforward, and it took a lot of time and iterations to get to this method, but we found that this is the best way to get to make the GeoGrid work. So we had also to implement a new corner handling algorithm to populate data here in the corner region. So this is based on Zerukat and Alan from the Met Office. So if we are here on panel 1, and we have to populate the corner region of panel 1, which is here the squares and the triangles. They describe really nicely how to do that in their paper. So basically, it is more or less straightforward to get the square points here because they are surrounded by well-defined data, and you can simply use a Lagrangian interpolation, a 1D Lagrangian interpolation to get the value of the 3 squares here and these squares here as well. We have found some issues with how to define that data at the triangle points. It wasn't very straightforward to get the correct data here, even though if you look at it, it will look a problem with like each point is surrounded by well-defined data, but it was not straightforward to get the correct data, and the sensitivity tests were finding some issues with how we approach this problem. And one last issue is basically breaking down the shallow water solver to apply flux averaging and bypass all the edge handling code. So this is basically the shallow water, a snapshot of the shallow water solver and different snapshot for the edge handling code. So why we have to do flux averaging over the tile edges? So imagine we are here on tile B and we are trying to compute the fluxes from B to A. So we have these points here. If we take this one layer here and we have the data here from flux A. So on the kinked grid, we can compute the flux here from B to A using these points. If we are on this face here, we have exactly the same points from tile B, and since our traction scheme is free of directional bias, we get the same values when we compute the fluxes. So basically the fluxes here at the edges are the same. So we don't really have to do anything, and everything is basically conserved inherently in the code. So when we consider the GeoGrid remapping algorithm, basically these points here will now be located along the extension of the great circle line. So when we compute the fluxes here from B to A, we will compute them following this line here, which will be different if we are on face A and are computing the data following this line here. So naturally, these points or these fluxes will be different if we are computing them from on each face. So what we are doing here, basically, if we compute the flux on each face and then we send it to the other face and we take an average. This is not optimal, but at the moment it introduces a lower order discontinuity, but at the moment we find it that it's negligible and it's not a big issue at the moment. So we have performed a lot of idealized test cases. I will show you a couple of them here today, and all of them are documented in this change paper that's available in December 2023. And here are the error norms that we were able to compute for some papers, and some of these idealized test cases are very standard test cases. So I will show you the results, for instance, for case 2, which is a very standard test case, the steady state geostrophic balanced flow, which will test the complete nonlinear shallow water equations, and you can have different axes of rotation to study different effects if you are interested in. So what you see here is a 200-kilometer simulation on the kink grid on the left and the geogrid on the right. So this is 200 kilometer. What you're looking at is the meridional wind, which basically in this case should be 0. So any deviation from 0 is errors. And you will see here in this graph how the errors are being built up over simply 5 days of simulation, the L1, L2, and L infinity. You can see here they start to be generated at the edges, and then they travel and basically contaminate the interior of the simulation, basically driving all the error norms all at the same time. If you look at the results on the geogrid, you can see that we are free of this noise, although you can see some noise that I will discuss in the next slide. So here's another way to look at these results. This is the difference in surface pressure. So any deviation from the initial field is basically an error. So I'm showing you here the results at day 1, day 3, and day 5 on the kink grid, and the same days on the geogrid. And you can see here the effects of grid imprinting. This is at 200 kilometers after 5 days. So it's not only local, it's also contaminated the interior of the field. You can see here some noise in the geogrid, but then we took a closer look at this noise, and it was a second order noise. Basically, what you see here, a convergence of error plots for L1, L2, and L infinity, and we are able to get a second order accurate solution for the geogrid, which is the same as the advection scheme that we are employing. So the noises that we are seeing the geogrid are okay. This is really nice because the geogrid, it will really get us the solution that is the same order of accuracy of the advection scheme. So there are a lot of tests, and I will show now the Rossby wave here, which is one of the most strenuous test cases for a dynamical core. It will test its ability to preserve robustness and symmetry and accuracy. So the more we integrate, the more we inject numerical errors in the solution that will basically break up this wave. And the errors can be basically developed or introduced because of many reasons, like truncation errors, rounding errors, model formulation, data interpolation, like edge handling or grid imprinting. So a normal test case for a dynamical core in literature is 14 days. So we say dynamical core past this stage can maintain a Rossby wave for 14 days. Here, the original FE3 actually does a really nice job, can maintain the wave for around 85 days, 90 days, where this wave start to break on the kink grid. And for the geogrid, we are able to extend this Rossby wave for more than 100 plus days to break at 105 days. So this was really a nice improvement that we got when using the geogrid. The colliding modon test case is a really nice test case, also very hard to make it work, especially over a corner. So you will have two modons here that are traveling, one to the east, one to the west. They meet in the middle, they exchange vortices, they travel back, and they meet again, and they have to come back to their initial solution. So this is also a stress case to test the ability of a dynamical core to simulate vertical flows. And you can do this test like this animation here, or you can also rotate the grids 45 degrees and make these models go over a corner, and such as the results that we have in this paper. So if you are a dynamical core developer, try this code. It will really show you some imperfection if your code, and it will make your code much more accurate. So for the last case, I will show the 3D baroclinic test wave. This is a 3D test case using the non-hydrostatic solver of FE3. So basically, you will have a baroclinically unstable atmosphere with a perturbation in the north that you can see it's being developed here. So we should not see anything or anything happening in the southern hemisphere. So if we take a look at, so this is at 200 kilometer, we will simulate this for 9 days. On the left, we have the kinked grid algorithm, the original FFC, and here we have the GeoGrid results. And you can see here in the southern hemisphere how the errors from kinked grid are being generated, and they grow with time. And then at the end, you will see, you will see these errors, how they grow in time, and they become, compared to the GeoGrid, you can see here the southern hemisphere is free of all this noise that you can see here. So we will basically unfold this field and then look at the whole map at 200 kilometer, 50 kilometer, and 13 kilometer. So this is exactly the same animation, just to look at the whole field. And you can see how this starts to develop at the 200 kilometer very early. And you will also see it at 50 kilometer and 13 kilometer. So basically the kink naturally become more pronounced for high resolution. So we expect to see a lower order noise for higher resolution simulation, which is what we see here, but we still see some noise. In the GeoGrid, all the fields are free of this noise. So not only the southern hemisphere, also away from the main signal, you will see some noise here, basically in the northern hemisphere as well. So basically employing the GeoGrid, so we have implemented this GeoGrid algorithm in FE3, and deploying it will greatly reduce grid imprinting in our code, and in some cases eliminate it. So we have seen in some cases that we are able to reduce the error norms up to 1 order of magnitude in some cases. And we can get the real order of accuracy of FE3 advection scheme. We found that the dispersion and dissipation properties are not changed. So you might argue that maybe we are basically losing like diffusing a little bit, or it's more dissipative, or the main signal is diffused a little bit. That was, we have one test, a splash test, that will show that the main properties are still conserved. So we are not basically disrupting the main signal in the flow. And this will be one fundamental algorithm for the future development of FE3 on GPU. So basically, you can safely say that robustness and accuracy has increased using this code. So at the moment, we are working on improving its performance, which is not too straightforward. The code is around 40% or 50% slower because of the extra communication and the remapping algorithm that we are employing at the edges, but this is still work in progress. And we will test more realistic test cases to see how real models will behave with this algorithm. So by that, I conclude my presentation, and happy to take any questions. Thank you.
Thank you so much. I'm going to take over the screen and display the questions document, and I just put the question document in the chat as well for anyone that has the questions. Are you able to see the question documents on the screen now?
Yes, I can see.
Perfect.
So yeah, I see the first question, how expensive the GeoGrid is. Yeah, so it is actually pretty expensive because if we are comparing it to the original algorithm, the King Grid, where we basically run everything on the King Grid, we can simply for the King Grid, we can copy the data from a neighboring processor and continue the integration. But for the GeoGrid, we have to copy the data, do the remapping, and then at some point stop and average all the fluxes. So for instance, for the case that I showed, the 3D non-hydrostatic solver test case for the pyroclinic test case, it was around like 40% to 50% more expensive. And I have to say, we have to spend more time working on this. So we are not currently working on this at the moment, but it will be something that we will pick up in the near future to basically try to optimize it as much as possible to basically try to minimize this overhead before we push it out to the public. So how are the boundary conditions and microphysics handled between the parent cursor grid and the telescoping grid? So if I understand the question correctly, basically the boundary condition of on the nest, we do a linear interpolation in space from the parent grid to the nested grid to fill the data for the boundary conditions on the nest. And the same will go to every level of grid nesting. So if we have, so each nest will behave similarly to its parent. It will take the data where from which it resides and then do an interpolation and fill up the boundary condition of. So if it's related to the nests, we already have that in the public release with the telescoping nesting already implemented and ready to be used. For the GeoGrid, the algorithm is ready, but from a computational standpoint, we are trying to optimize it as much as possible before release it. So at the moment, we don't really have a date to release this algorithm. Yeah, I think so. Like the update will be the same for the UFS. So once we push the GeoGrid code to the public repository on GitHub, we basically push that to the official repository on GitHub. We can do exactly the same for the version of FE3 that's being used in the UFS. So basically very similar to what we did with the telescoping nesting. So I don't know how that will affect CCPP, but if I so CCP, if I know it, if I understand this correctly, is the physics package used in for the UFS. So this is not. I don't think it will affect anything external to the dynamical core, as this is basically will be limited to the dynamical core, and all the remapping calls will be written inside FE3. So you might able to use the remapping calls and the GeoGrid the remapping calls for other fields if you wish to, but basically this will be an internal model in FE3 that's being developed. So. Yeah, you're welcome. Yeah, thanks.
All right, we are just about at time. So thank you so much, Dr. Mualim, for your presentation today. And we'll be posting this recording slides on the UFS website. Thank you, everyone.
Okay. Thank you, Alex. Thanks, everyone.